Force and motion. Rolling, jumping, creeping, slithering, spinning. Introduction. Each word above describes how objects can move. Some things move in a straight line, such as a ball rolled to you along the ground. When you kick the ball in the air, it flies in a curved path and then bounces on the ground until it stops. A merry-go-round revolves in circles when lightning strikes in a jagged path. Motion is everywhere, and it is vital to life. Think of how your heart's movement keeps blood flowing throughout your body. In this book, you will learn what makes things move, stop, change direction, and change speed. Motion needs a force. In order to make something move, a force is required. Lifting, pushing, and pulling are all types of forces, and those forces come from countless sources. Sometimes a person can provide the force. If you lift a stack of books, push a broken down car, or pull on a rope in a tug of war game, you are the source of a force. Lift, push, pull. Machines can also produce a force to move objects. The power of a huge engine can produce enough force to propel a massive rocket into space. A car's smaller engine makes its wheels spin, moving the vehicle down a road. Motors and cake mixers, fans, and blenders use electrical force to make things move. Nature can act as a force too. For example, breezes make leaves dance in the treetops. Ocean waves make boats bob up and down. Forces deep underground can cause earthquakes that make the ground tremble and destroy buildings, bridges, and highways. Earth's crust is made up of moving plates. These plates can shift in various ways. The force of this shifting causes earthquakes. The laws of motion. Much of what we know about motion comes from experiments and observations made by scientists hundreds of years ago. The Englishman Isaac Newton is especially famous in this regard. You may have heard of him as the man who was sitting under a tree when the apple fell and hit him on the head. The story goes on to tell how this event led to the theory about gravity, the invisible force that causes things to fall toward the ground. Actually, Isaac wasn't hit on the head by a falling apple. That is a myth. But over time, he observed that objects always fell down toward the ground. These observations, combined with his curiosity, drove him to study gravity. Newton's first law of motion. Isaac Newton is best known for writing 3 laws of motion that explains how all things move. The first part of Newton's first law says that an object at rest will remain at rest unless a force acts upon it. For example, your bike will stay parked where it is unless someone or something moves it. The second part of the first law states that an object in motion will continue in motion at the same speed and in the same direction unless a force acts upon it. So if your bike is rolling, it will continue moving just as it is until you pedal faster, coast, brake, or turn. If a force, such as a headwind, pushes from the opposite direction of the bike's motion, it will slow the bike or stop it completely. If a force, such as a side wind, is applied to one of the side of the moving bike, the bike will change direction. Sir Isaac Newton, 1642 to 1727. Isaac Newton was born on Christmas Day in Woolsthorpe, England. He lived on a farm with his grandmother. He had little interest in becoming a farmer and chose instead to study math and science at Trinity College, which is part of the University of Cambridge in England. At age 27, Newton conducted experiments with light and was the first to suggest that light was actually made up of all the colors. He eventually became one of the most famous scientists of all time. Word-wise. The word law often means a rule made by a government that people must obey. In science, a law is a statement about results that always occur under certain circumstances. Whether an object is at rest or in motion, it has inertia, the tendency to keep doing what it is already doing. Unless a force overcomes the inertia of an object at rest, it will not move. Similarly, an object in motion will keep moving unless a force stops it. So inertia is the reason an object at rest stays at rest, and an object in motion stays in motion, until a force acts on it. Newton's first law of motion, sometimes called the law of inertia. An object has inertia when it is at rest, and it also has inertia when in motion. In either case, a force is required to overcome inertia and cause motion to start, stop, or change. Newton's second law of motion. Why is it easier to move a small rock than a boulder? Well, the boulder has much more mass. Scientists define mass as the amount of matter in an object. Newton's second law of motion explains that an object's motion depends on its mass and the amount of force being used against the mass. Since a large boulder has much more mass than a small rock, much more force is needed to overcome the boulder's inertia. Much less force is required to make small rocks move, stop, or change direction. The train has a large mass and a high speed, so it has a lot of momentum. It would take a very strong force to slow or stop this train. While mass is important to motion, speed matters too. Speed is a measure of how much distance is traveled in a particular amount of time. The faster an object is moving, the more force is needed to stop it. Think about a runaway locomotive speeding down a track. It has both a lot of mass and a lot of speed. A great deal of force will be required to overcome the inertia of the train's motion and make it stop. This law of motion explains why trains cannot stop suddenly. Scientists measure the amount of inertia as momentum, the force that keeps an object moving. Wordwise. Velocity describes an object's speed and a certain direction. Scientists calculate momentum by this formula: mass times velocity equals momentum. Newton's third law of motion. Newton's third law of motion says that for every force or action, there is an equal and opposite reaction. Think of forces in pairs. When you push or pull on an object, the object sends an equal push or pull on you in the opposite direction. So if you lift a 9 kilogram, 20-pound box, the box is pulling downward with an equal force of 9 kilogram, 20 pound in the opposite direction. The third law of motion also explains why a balloon full of air goes flying when you let it go without tying it. As air rushes out the open end, an opposite force pushes on the other end of the balloon, making it fly. Similarly, a rocket's upward flight is an opposite reaction to the hot exhaust shooting downward from the powerful engines. As air rushes out of the open balloon, arrow A, an equal force pushes in the opposite direction, arrow B. And which direction will it fly? If you said towards B, you were correct. Types of forces. Earlier, you read about lifting, pushing, and pulling, as well as machines and nature are all being sources of forces. Read on to learn about several additional important forces. Gravity. Isaac Newton observed that all objects in the universe attract other objects due to gravity. This law is known as a universal law of gravity. The strength of the gravitational pull between two objects depend on their masses and distance. Greater masses have a stronger pull. The longer the distance between them, the weaker the pull. Mass, distance, and gravity. In which situation is the gravitational pull strongest? And which situation is the gravitational pull weakest? A. Two small masses, short distance. B. Two small masses, greater distance? C, two large masses, short distance, or D, two large masses, greater distance? If you said C is the gravitational pull the strongest, then you are correct. In which situation is a gravitational pull the weakest? The answer is B. Understanding the effects of mass and distance on gravity will help you understand why objects fall to Earth rather than toward each other. Imagine you are standing next to a large building. Both you and the building have mass, so you both have gravitational pull. The building has much more mass, so it pulls you more than you pull it. However, both you and the building are standing on Earth, which is far more massive than either you or the building. Earth's gravity is so much stronger that it has much more gravitational pull on you and the building than you and the building have on each other. The gravitational pull between you and the building goes unnoticed. This is true of all objects on Earth. On Earth, an object's mass is measured as weight. The greater the mass of an object, the more the force of gravity it pulls on it, and therefore, the more it weighs. If you are in space twice as far from the center of Earth as you are now, the gravitational pull would be 1/4 as strong. You would still have the same mass, but you would weigh 1/4 as much as you do here on Earth. Earth seems huge to us, but the Sun has much more mass than Earth or anything else in our solar system, and as a result, it has enough gravitational pull to keep all the planets from flying off into space. Instead, they all orbit the Sun. Remember, both mass and distance are important aspects of gravity. So, while the Sun has a greater gravitational pull than Earth, the distance between your gravitational center and Earth's gravitational center is much less than the distance between your gravitational center and the Earth's gravitational center. So you remain pulled toward the Earth, and that is a good thing. If Earth were too close to the Sun, you would be pulled toward it. Friction. Friction is an invisible force that slows down moving things. Friction changes motion energy to heat energy. As an object gains heat energy due to friction, it has less motion energy, so it slows down. The most familiar kind of friction is sliding friction. When you rub your hands together firmly, they create sliding friction, which produces heat energy. That's why your skin warms up. A rolling bowling ball experiences another kind of friction, rolling friction. Rolling friction will slow down a moving object, but not as quickly as sliding friction. If you shove a heavy box across the floor, it will soon slow down due to the sliding friction. But if you place rollers under the box, it will move farther when shoved since rolling reduces friction. Did you know? Rough surfaces exert more friction against each other than smooth surfaces do. Putting a lubricant such as oil or grease between two surfaces will reduce friction. Another kind of friction, fluid friction, occurs when an object moves in contact with a fluid such as water or air. It is easier to move your finger through water than honey because honey creates more fluid friction than water. Engineers design airplanes to reduce the drag caused by fluid friction with the air. Fluid friction can help objects move more easily, such as a puck floating on air in an air hockey game. However, objects experiencing fluid friction will slow down and eventually come to a stop. Think about it. Imagine that you wanted to race your friends down a snowy hill. How could thinking about friction help you win the race? Force, motion, and work. In science, you do work when you move something. If you push against a wall all day long and it doesn't move, You have applied a force, but you have not done work. The amount of work you do depends on two things: the distance the object moves and the amount of force it takes to move it. The farther you move an object, the more work you do, and the more force you apply to a moving object, the more work you have done. Scientists measure work by multiplying the distance an object moves by the force used to move it. Force times distance equals work. 4 blocks, no baby. Most work, 4 blocks with baby. Least amount of work, 2 blocks, no baby. 2 blocks with baby. It takes less work to push an empty stroller than a stroller with a baby in it because an empty stroller has less mass. Also, pushing the stroller 4 city blocks requires twice as much work as pushing it only 2 blocks. Energy. If you have ever pushed a stroller or lifted a heavy box, you know that it takes energy to do work, and sometimes a lot of energy. In fact, energy is defined as the ability to do work. The more energy you have, the more work you can do. Potential and kinetic energy. Energy comes in 2 basic types: potential and kinetic. Take a rubber band, for example. When you pull it back, it has potential energy. The energy is stored and ready to use. The farther back you pull the rubber band, the more potential energy it has. When you let go, you convert that potential energy into kinetic energy, and the rubber band flies across the room. Energy in motion is kinetic energy. Can you guess which type of energy a tank full of gasoline has? Fuels such as gasoline have potential energy. They have energy sources. Burning gas to make a car move converts that potential energy into kinetic energy. A full tank has twice as much potential energy as a tank that is half full. Think about it. Why can't a motorcycle that is out of gas be ridden? Well, think about potential and kinetic energy. The food you eat also has potential energy. Plants get energy from the sun, and animals get energy from eating plants and other animals. When you eat and digest food, you store up the energy. That energy makes your heart pump and makes your lungs expand and contract. Stored energy also makes your muscles work, allowing you to run, jump, speak, write, and smile. Energy transfer. Energy can be changed or converted from one kind to another. Energy can also move from one object or place to another. Converting and moving energy is called energy transfer. Solar energy can turn into stored energy in plants through photosynthesis. The stored energy in foods can be transferred to your muscles and converted into motion energy in your arms. And then the motion energy in your arms can be transferred to moving drumsticks. The moving sticks can make a drum vibrate, creating sound energy. Chemical energy in batteries can make a toy robot move. Some of the energy might be converted into sound energy to make sounds. The energy may also be converted into light energy to operate colorful lights. What other examples of energy transfer have you read about? Conclusion. You have learned that it takes force to make things move or stop, and that force can affect the direction and speed of a moving object. You read about Isaac Newton's laws of motion and how the mass of an object is related to the force needed to make it move. Simple pushes and pulls, as well as lifting, are examples of force. Other types of force include gravity, friction, and magnetism. People can exert a force, as can machines in nature. You have also learned that work is done when a force moves an object over a distance. It takes energy to do work. This energy is either potential, stored, or kinetic motion. Energy can be transferred by moving it from one object to another or by changing it from one type of energy to another. Observe all the motion in your world. Which forces are making things move and which forces are affecting those moving objects? Soon you will discover that forces in motion are all around you.